Thomas Trinkle. I'm going to be talking about elastomeric graphs. So this was in a paper, methyl acrylate-based photoelastic as tailored biomedical for artificial vascular grafts. So basically they're making heart grafts with 3D printing process. So their goal was to create a blood vessel using 3D printing. And their two key focuses in doing this were, one, what are the mechanical properties of this blood vessel, and then regardless of what your mechanical properties are, if it's not biocompatible, it won't do you much good. So they're looking at that also. So they primarily focused on 3 different materials. So you got CEA, which is polycyanethyl acrylate. You have ETA, which is ethyloxylated trimethyl propane, and PEGDA, as Jordan said earlier, is polyethyl glycol diacrylate.
So the first one is just crazy glue.
So the first one is their primary material, and then the last two are what they're trying to use to bind it together to get better mechanical properties. So they were looking at biocompatibility in human cells, and then the elastic modulus of the blood vessels. They talked about using other mechanical properties, but they felt like this was the best one to actually look at. And then they used a laser scanning microscope and a tensile testing machine. So their first key study was mechanical properties. So as you can see, this is what they measured as actual. So they took it from a sheet, and then they did the same exact measurements on the sheet blood vessel as they did their printed. They took 5 different printed articles and did the tensile test on it. And they showed that the only one that was possible was this C, which was 15% the CEA, 14% the PEGDA, and then, I don't know how it's possible, but 80% ethyl hydroxide, which is over 100%. The only difference between this and this was this is only 70% of the ethyl hydroxide, and then this was not at all used. Now this ABC that trends downward was the percent of the strain break. Now they said that for most of the sheet tests that they had done, they were between 150 and 100%, but they never got their actual printed to be over 100%. C, which is this one here, was not nearly as high as the others, but they felt like this didn't really matter. They were primarily focused on the elastic modulus. So as PEGDA was increased, the elastic modulus increased. Now, what you did see is they didn't use ETA on the previous study, and that was because of this one. So they were trying to find biocompatibility. So A and B were using the ETA. This is 5%, this is 10%. So it was not very biocompatible, so they kind of threw it off to the side and said, we don't want to use that at all. C and D is where they put the PEGDA into the sample, and they increased it. It was about the same percentage as the previous mechanical study. And so you can see that D was very biocompatible. So they felt like if you increase PEGDA, one, you get increased mechanical properties, but you also get increased biocompatibility. So, in summary, an increase in PEGDA increases both mechanical and biocompatibility. It seems to be very promising when it comes to making blood vessels. So they felt like this was really good. The reason they were doing the study is a lot of the current methods to create the blood vessels using actual human parts and stuff coming from the person that is getting it is they don't seem to actually implant into the person as well. Their biocompatibility is not very good, and the success rate is not all that great. And so it has a pretty, in 3D printing, additive manufacturing, it seems to be a pretty promising idea. Personal critique. They didn't really discuss the testing method. They did, however, say that they looked at a whole group of materials They kind of did what we're doing in this class. They looked at previous research papers and tried to figure out exactly what they wanted and only pick the certain materials that would be good for their application. And this would be good to carry the information forward so that as more materials are developed, you can kind of put those forward and understand how much better biocompatibility you can get in mechanical